So next we're going to explore the effects of temperature on spontaneity. Okay, so the effects of temperature on at what temperature then would things be spontaneous or non-spontaneous? Enthalpy and entropy are virtually temperature independent, meaning they do not depend on the temperature, right? So we're going to bring in Gibbs free energy and use this equation of delta G equals delta H minus T delta S. Remember, this temperature has to be converted into Kelvin to use with S because S has units of Kelvin in it from our chart. Okay, and so that can be used to help us understand what G will look like and whether things are going to be spontaneous or non-spontaneous at different temperature scenarios. This chart here is just sort of a summary chart, and I want to make point out a few observations for you. Notice that for 3 and 4 I shaded things in gray. What I want you to see then is that what I've done for the gray part is to memorize the gray part instead of needing to memorize both of these. Okay, so let's go through this really quick. So what I want you to see is that if I have a delta H sign of negative, my delta G is negative. Positive, positive. Looking at the gray shading for this memorization piece or trick, H is positive, G is positive. H is negative, G is negative. So if we use the gray, and then for 1 and 2, the standard piece there, we know that when we know the sign of H, we can assume the sign of G to be the same, and then there'll be some patterns that fall out. So now we have 2 different setups. We have 1 and 2, which the signs are flip-flopping, negative, positive, negative, positive, negative, positive. Or, again, using the gray as our piece of focus, for 3 and 4, we have same sign, same sign, same sign, positive, 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 negative, negative, negative. Okay, so keeping that in mind, let's look at then what we know. If our sign is going back and forth, right, negative, positive, or positive, negative, positive, then we know we can say that it's spontaneous or non-spontaneous all temps. So if our signs are flip-flopping, we can say all temps. Okay? If our signs are the same, then we can say it's either spontaneous or non-spontaneous at low temps, because we're going to memorize the gray. Okay? So, that being said then, now we got to determine how do we know if it is spontaneous or non-spontaneous. So, we're going to first say, okay, look at this. This is negative, positive, negative. So it's going to be at all temps, right? Because the sign is flip-flopping. And I'm going to say, look at my G sign, the sign of G, to know if it's spontaneous or non-spontaneous. And because G is negative, it's spontaneous. And G is positive, it's non-spontaneous. Similar, right? Except for temperature difference, right? When I have a positive G, and my signs are all the same, we're going to say positive is non-spontaneous, positive up here was non-spontaneous, so that's true. Okay, non-spontaneous when we have a positive G, spontaneous when we have a negative G. And then if the signs are all the same, we would say, oh, the G is positive, so it's non-spontaneous at low T. The G is negative, and the signs are all the same, so it's spontaneous at low T. Up here, the signs are flip-flopping, so then we know it's spontaneous at negative G. The signs are flip-flopping, so we know it's non-spontaneous at positive G. Let's explore a little deeper. Here we have a formula, delta G equals delta H minus T delta S. We have used this before. We're going to use this to analyze, and the math in the grid back here, to figure out how to predict what we think will happen and at what temperature. Okay, so this is example 11 or 33A from your textbook. Okay, we have discussed the effects of temperature change on spontaneity of the following reactions at 1 atmosphere. So that's standard pressure. Okay, so now we're going to evaluate what our signs are for H, S, and G. So H, S, and G. From this problem, we see that H is positive, S is positive, and we remember from the chart we looked at before that we know if H is positive, then G is going to be positive based on the way we're going to memorize that chart. So therefore, we can say that all the signs are the same, so then we know that it's going to be evaluated at low temperatures. And because we know delta G is positive, we can say non-spontaneous. So the answer to this would be non-spontaneous at low temperatures. Non-spontaneous at low temperatures. This problem is asking us to tell us the temperature at which, when G goes to become 0, for the above reaction, really this reaction, I just had to move it for space. Explain the significance of your answer. So we're looking for a temperature here. So we're going to take this algebraic formula and we're going to manipulate it to solve for T so that we can get a temperature. So the first step here is going to be to place a 0 in for G, like it says here, when G becomes 0. Now we're going to solve for T. To do that, the next thing we're going to do is we're going to subtract delta H from both sides. So when I subtract delta H from this side, remember we're trying to get T by itself, so algebraically I'm going to rearrange. I get delta H disappears on this side, and it's negative delta H. Next thing we're going to do is solve for T is divide by negative delta S. So when I divide both sides by negative delta S, I end up having negative delta H over negative delta T equals, negative delta H over negative delta S equals T. And then these signs would cancel, so the final piece we'd get is T equals delta H over delta S. Now we're going to plug our values in here. So we plug in our H value and our S value. Remember that anytime you're using an entropy, an S value, you want to check its units versus, especially when you're using it in combination with a G or an H value, and Gibbs free energy, or an enthalpy value. Are the units the same? Okay. Nope, we have kilojoules and joules, so we'll need to do a conversion. So we're going to go over here and we're going to convert 168 joules. Okay, normally we go to kilojoules by taking the fact that for every 1 kilojoule is 1,000 joules, so we got that converted. And I'm going to convert that, and we're going to change this unit into the proper unit of kilojoules so that we can divide these two. When we would get that, we get 4,945 Kelvin. So that's the T when G becomes 0. Now let's do this last piece, explain the significance of your answer. So this piece here comes from the part we did part A, where we evaluate H, G, and S, and we discovered that the temperature will be non-spontaneous at low T. Or should I say the reaction will be non-spontaneous at low T. So because of this evaluation, then we can finish off this question with the piece that says explain the significance of your answer by saying that it's going to be non-spontaneous at T less than, because of low, 4,945 Kelvin. Okay, another example, same kind of thing. We're going to evaluate H, S, and G for their values and their signs. So looking at this here, we can see that H is negative, S is negative, and the way we're going to memorize this, then we know that if H is negative, if H is negative, we're going to make G the same sign. Okay, so we have here understanding that we have all the same sign. So let's look at that. So all are the same sign, so therefore low T. And then we know, remember, because of H, S, and G are all the same sign, then we're looking at low T, not all T, but low T. And we know that delta G is negative, so it's going to be spontaneous. We would say then this reaction is spontaneous at low temperatures. And here we are doing the math to answer that same type of question at what temperature. So that's the formula that we derived at from rearranging our variables. When G becomes 0, we did that math on the last problem to show how I got this algebraic formula. Plugging in my value for H, plugging in my value for S. Are the units the same? They are, so I don't have to convert. I get 5,199 Kelvin. So now let's do the last piece. This is the first piece. This is the temperature answer. Now let's explain the significance of that. This is the work that we did on the first part of question 33B. This is 35B. It says refer back to 33B. So with the same problem, we did this a moment ago. We evaluated that all the signs were the same, so therefore we knew it was spontaneous at low temperatures. Therefore we can say that this is going to be spontaneous at temperatures less than 5,199. Spontaneous because it's G negative, and then T less than 5,199 because we're looking at low temperatures. Okay, similar example. This is just part 33C from our textbook. So we're looking at the fact that we know H is positive, S is negative. Remember, the way we're going to memorize that chart is we're going to always have H and G be the same sign. So H is positive, G is positive then. All signs rotate, positive, negative, positive. So therefore, we're going to consider it at all temps instead of low temps when they're all the same side, we do low temps. When the signs rotate, we do all temps. And we know that G is positive, so when G is positive, it's non-spontaneous. So we would not need to do a calculation here because it's never going to be spontaneous with the temperature change, because we know it's going to be always non-spontaneous at all temperatures. Last example is example 12 from your textbook. This is just going to have you do a calculation instead of giving you the values. So based on this formula, it says red phosphorus is formed by heating white phosphorus. So I take white phosphorus, I heat it up. We could put a triangle here to represent heating over the arrow. Makes red phosphorus. Okay. Says we want to know calculate the temperature which two forms are at equilibrium. So that's when G is 0. All right. So that's how I know I get to use that formula here. So we're going to have to calculate the value because we don't have them. These would be yellow chart numbers or thermodynamic table numbers, right? So I have, I'm going to take red minus white. So I'm going to take this red for H is negative 17.6 kilojoules, and the white for H is 0. So I subtract those two. This is the stuff we've been doing all unit, and we did delta H last unit. Similarly, we're going to take this for S. Right, so we're going to take the entropy of red phosphorus, 22.4, subtract from, because remember we're going to do, just like with H, we're doing products minus reactants, right? So this is my product, this is my reactant, that's why red's first. And then we're going to subtract off the 41.1 joules per mole Kelvin for white phosphorus, plug them into the formula that we've been using for the last couple examples. Are the units the same? Nope, so we're going to have to convert. So we do a quick conversion here. And then we can plug in the corrected value so that we can actually finish the math off. And we end up getting, we end up getting 962 Kelvin. And it asks for the temperature, not an explanation. So that problem is complete. If it would have asked for an explanation, we could have went through the process of evaluating H, S, and G, and then applied the skills that we've been learning from this unit. That concludes this lesson for this part of our unit. Have a fantastic day.